Hi guys, welcome back to my mathematics tutorial. Again, my name is Peter C. Jr., your math tutor and an instructor of mathematics at the University of Liberia. In my today's lesson, we will be continuing on differential equations, and like we started in previous lessons with reducible to variable separable method. So we said, what if we have a differential equation dy by dx that has a function f of ax plus by plus c, like you see on the board. What if we have a function of this form? And then we try to separate the variables. At first, we cannot. So what do? So we bring in some substitution. That is, we substitute this entire expression with a variable, just a single variable, such that when we differentiate both sides of that new equation that we formed, we can now bring in the value of dy by dx and then be able to separate the variables within this differential equation to find the general solution of the dE. So we want to solve the last two examples under this topic. We've solved several problems, I think like 10 problems under this topic alone. So we want to solve the last two examples. This is second to the last. Dy by dx plus 1 equals to e raised to the power x plus 1. So had this just been e raised to the power x, we can easily separate the variables and find the general solution. But this is e raised to the power x plus y. So we must substitute x plus y with a single variable. So we say let a variable u equals x plus y. So we differentiate both sides of the equation. Remember, u and y are functions. So when you differentiate u, you must attach a derivative notation. That is, the derivative of u is 1, so we attach du by dx. Is equals, the derivative of x is 1, the derivative of y is also 1, but because it is a function, we attach dy by dx. What's next? Next thing is for us to solve for dy by dx. So we send this 1 across to u all over dx. Minus 1 is equals to dy by dx. What's our next step? We'll go back to the problem to replace dy by dx. But since we see that dy by dx plus 1, dy by dx plus 1 is just du by dx, we will just replace this entire side with du by dx equals e raised to the power x plus y is just u. Now we cross multiply, so we have du is equals to e raised to the power u dx. So what do we have? This is x and this is u, so we must get rid of this e raised to the power u. We can multiply both sides by 1 over u, e raised to the power u. So multiply both sides by 1 over e raised to the power u, we will have 1 over e raised to the power u du, or equals to dx. Now we can integrate. So e raised to the power u, we send in the numerator, we're going to have e raised to the power minus u du equals to dx. So we know that the integral of e raised to the power x dx is just equal to, or let's say we have, okay, let's just use x. So the integral of e raised to the power x dx is just equal to e raised to the power x plus some arbitrary constant c, right? But in general, the integral of e raised to the power, we know that the derivative first of e raised to the power x, e raised to the power ax, is just equal to what? You rewrite e raised to the power ax, and then you differentiate the power, which will just give you a, right? So for this one, it is a reverse. So instead of just getting a e raised to the power ax, this one now, e raised to the power ax dx, will just give us 1 over a e raised to the power ax plus some arbitrary constant c. So what does a represent? A is representing this negative that is right there. So now the integral of e raised to the power minus u is just minus e raised to the power minus u equals the integral of dx is just equal to x plus some arbitrary constant c, right? So what else? 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 So now what we can do is to just further simplify. So if we multiply this entire thing in fact by negative, we're going to have e raised to the power minus u minus x minus c. So minus c is just c, because whether it is negative c, positive c, it's still a constant. So what is u? We bring back the value of u, which is x plus y. So this is e raised to the power minus x plus y, or equals to minus x plus, let's say, minus c. So we just take in general now plus c. So what do we do next? We can take the ln on both sides, because we know that the ln of e raised to the power x is just equal to x. So we can take the ln on this side and take the ln on this side. So we take the ln e raised to the power minus x plus y equals to the ln of minus x plus c. So we take the ln on both sides. Ln of e raised to the power, e raised to any power is just equal to that power. So it's x plus y equals to the ln of, I'll write c first, minus x. So what next? We can further simplify that expression. That is, if we multiply both of them, we're going to have minus x minus y equals to what? Ln of c minus x. So we want to solve for y. What do we do? So minus y is just equal to x plus the ln of c minus x. So we can get rid of this by just multiplying this whole thing by -1. So y now will be minus x plus the ln of c minus x. So there's our general solution for this problem. If you like, you could also stop just right here. You could stop right here. It's not a problem. So let's solve the last problem under this topic. So this problem says x plus y minus a over x plus y minus b times dy by dx is equal to x plus y plus a x plus y plus b. So for this problem, we see that x plus y is repeating everywhere in both on both the left and the right hand side of the equation. So x and y are the two variables, right? So if we substitute x and y with a single variable, we will have a single variable in here, likewise a single variable in here. So we can say let x plus y equals to some u. What's next? We differentiate both sides. So this is just 1 plus also 1. So we attach dy by dx. And this is also 1. So we attach the u by dx. We solve for dy by dx. So we send this one across. Dy by dx is just equals to the u by dx minus 1. So we can now replace within the problem. So let's put this thing somewhere, x plus y. So u equals x plus y, so that we take note of it. Okay. So we now replace x plus y is just u. So it's u minus a, u plus u minus b times, what is dy by dx? It's just equals to what? The u, because we allow our u to be x plus y. We differentiated both sides, right? So dy by dx now is just equal to du by dx minus 1. Or equals the same thing here, u plus a or over u plus b. Okay. Now, at this point now, we want to make all of the expressions with u on the left-hand side and all of the expressions with x on the right-hand side of the equation, right? So to do that, we first get rid of this factor right here. So to get rid of this factor, we can just multiply the both sides by the reverse or the reciprocal of this. So it's u minus b or over u minus a, such that this factor can cancel. So we're going to have du over dx minus 1 equals u plus a over u plus b times u minus b over u minus a. What else? We send this one across, but before doing that, let's multiply on the right hand side first. So du over dx minus 1, u times u squared, u times b is minus bu, a times u is plus au, and a times b is minus ab, divided by u times u is u squared, u times a is minus au, b times u is positive bu, and then b times a is minus ab. So if this minus 1 goes across, it becomes positive 1. So this leaves from here. And then now we have to find the LCD. So it's like multiplying this denominator by this one. So what do? We have du. Let's bring it on this side. So we have du by dx is equals. So the LCD now is just u squared minus au plus bu minus ab. So the first, u squared minus bu plus au minus ab. So this time this gives us u squared minus au plus bu minus ab. So we simplify. Minus bu, positive bu, they go out. Plus au minus au also go out. So we now left with u squared plus u squared is 2u squared. And then minus ab is minus 2ab. So the denominator, we can factorize it, factoring by grouping, first two and last two. So in the first two terms, we have u squared au. So u is common. So we bring out u. So it's u minus a plus b is also common. So it's u minus a. So the du now by dx is just equal to, so this numerator, what is it? So we can factor out this numerator right here. So you have 2 and 2. So it's 2 coming outside is u squared minus ab divided by this guy down here now is what? What is common? So it's u times u minus a plus b times u minus a. So u minus a is common. So it's u minus a times what is left here is just u plus what is left here is just b. So our objective now is to ensure that we separate all of the terms with u and all of the terms with x. So let's cross multiply and see how we do that. So we have the u. Let's get this one. So we have u minus a, u plus b du, all equals to 2u squared minus ab dx. So we want to get rid of this expression because it is in u and this is x. So we can divide this out by 2, or let's just take u squared minus ab. And we just take u squared minus ab. So this and this cancel. So we are now left with u minus a times u plus b all over u squared minus ab du all equals to 2 dx. Integrate both sides now to find our general solution. Now, I think we should have just allowed this denominator, this numerator to just be in expanded form, right? But let's look there now. Let's try to solve that problem. So to do that, we want to expand this numerator such that at least we can have an expression that we can easily integrate. So u times u, so that u times u will give us u squared, and then u times b will give us bu, and then a times u will give us minus au, and then a times b will give us minus ab, divided by u squared minus ab. Du is equal to the integral of 2 dx is just 2x. So we can group the first term and the last term because we see u squared minus ab, u squared minus ab. So we group the first term u squared minus ab all over u squared minus ab dx or du now. Then we group the middle terms here, right? But this middle term here has u in common. So we can now say b minus a times u all over u squared minus ab du all equals to 2x. Okay, so we're still trying to integrate. So what's next? This gives us the integral of just du plus b minus a is a constant. So we factor it out, b minus a. And we have the integral of u all over u squared minus ab. So we know if we differentiate u squared, we're going to get some u. So we can say let some t equals to u squared minus ab. Then the t now will be 2u du. So this is just u, right? This is u du all equals to 2x. So since we need 2 right here, we can rationalize 2. So we say 2 and we say 2, rationalize 2, right? And then we will have the integral of du is just u plus 1 over 2 b minus a, the integral of 2u du is just equals to dt, and denominator is t, all equals to 2x. So we can further simplify or we can further integrate as well. So we have 1 over 2 b minus a. The integral of this is just ln of t, all equals to 2x plus some arbitrary constant c. So what is u? U was x plus y. So we have x plus y to be our u, plus So this is 1 over 2 b minus a ln of t. T is u squared minus ab. So u squared minus ab. So this t, right? T is u squared minus ab. Great. Equals 2x plus c. So we send this x across. We want to solve for y, or make y the subject. So we have y equals to 2x minus x. And then this now becomes minus 1 over 2 b minus a, the ln of. Now what is u? Initially u was x plus y. So since it is square, we square it. Minus ab, or equals to, plus some arbitrary constant c. So y now becomes 2x minus x is just x, minus 1 over 2 b minus a times the ln of x plus y raised to the second power minus ab plus some arbitrary constant c. So this is our general solution for this differential equation. So thanks ever so much for watching. Please subscribe to our YouTube channel and see you in our next lecture. So our next lecture will be on homogeneous differential equation. So we've solved up to 82 problems now on a differential equation. So we want to look at another method of differential equations that is called homogeneous differential equation and reducible to homogeneous differential equation. So thanks ever so much. See you. Don't miss class, please.